Okay, so today's video is going to be about quantum mechanics. And in quantum mechanics, we will talk about um, what do we talk about? Uh, yeah, wave particle duality. Our topic is wave particle duality. And in this, we will be talking about the wave and particle nature of light. So this is shown in different experiments. First of all, let me describe what is wave particle duality. It is the nature of, or wait, let me say it is the dual dual nature of light depending on whether it's observed observed not observed or observed or not observed. Okay, so if this is a definition in my way, many people can have different definitions, no problem. So the main thing here is that uh, it is the dual nature of light. Dual nature here, the important thing is dual nature. Over here I'll just put depending on experiment, the nature of the nature of light is talked about. Okay, so the first experiment is photoelectric effect. This experiment talks about the particle nature of light. Okay, and how will I write it is, I will write it in the form we talk about photoelectric effect, particle nature, and in this we will be talking about wavelength of, or a wave, which is nothing but energy photon. It will not be a wave, it will be particles, and these particles will be E equal hf. When they are traveling towards this, let's suppose we have a metal here. The energy which this metal needs is known as, we'll say it's Ek, the energy which, or we can say the energy with which it bounces off is Ek, or I will say kinetic energy. The energy with which it's attached to the metal is this work function. It's called work function, also known as this symbol. This symbol is also one given for work function. And as for the here, this frequency will, we can write E equal h of f. This will go to E equal h c over lambda. This is a best. This is a further example. Here you will notice something, that energy transfer is in discrete. How? This is said by the first equation, as per me, of the quantum mechanics, which is this equation, u of f, and this equation. This equation shows that energy can't be transferred in discrete, in the continuous form. It will transfer in discrete amount. Change or transfer in discrete amount. This is from the Planck's law. The first law, the law made by Max Planck. Then if I combine this equation, and this equation, I should get this equation. Or wait, let me see. E, or wait, I will not write E. H c over this equals to 1 by 2 mv square plus psi. And this is actually, it should be written like this. It should be written like this. Okay, now here this can be written as h of f equals to this plus 1 over 2 mv square, and this can further be written as E equals to psi. This is a work function plus 1 by 2 mv square. E of photon, electron. So then other than this, we have what else is here? Here you will not find light in wave. As I said, light cannot transfer in discrete amount. Here photon is taken as, of course, photon or light. Photon. And mostly the formula of the energy is written as E dot V. It's the same as saying joules, but it's because to convert it into joules, you would do to convert it into joules, it's E times joules times 1 over 1.6 times 10 to the power minus 19 equals to EV. Then you can also tell what joules what we need for the joules. We just multiply it with that. Okay, here then we can talk about, as we are here, we can also talk about energy spectra. Energy, the spectra, not energy spectra, the spectra only, the energy levels. Here, every arrow represents a change in energy. Every arrow represents an energy, and so on, whatever we have here. Okay, but the direction of arrow shows gain and loss of the particle or the electron, because electron is the one which is gaining. And the simple example we take is of hydrogen. Loss, gain and loss of energy of electron. Here the formula E equal hc over delta T. If I have a question that what when is energy energy uh, energy emission, energy loss, I would say energy loss more. When I talk about here, the key point is energy loss, because energy, the word loss shows that the electron decreased in level, decreased in energy level. Okay, so it cannot be the ones which rise in level, it has to be one which decrease in level. And from here, now that which has the most energy loss, we look at E equal hc over f in terms of wavelength. Let's suppose we'll talk about the one with the biggest wavelength will have the the one with the lowest wavelength will have the greatest energy loss. Here we see that it would be smallest wavelength, smallest wavelength, so smallest change. This is high, this is high. These are all up, so you can have this from 1 to this, and this. So I would say energy loss or energy loss is great when or the with the smallest difference. Here energy loss is great, huge amount. Then let's talk about the Schrodinger equation, or not Schrodinger equation, sorry, the Young's double slit experiment. Here we have some key points to look at. So first of all, let me describe this. This is x, this is x, and there's an equation for this which is n d equal lambda sine theta. If I'm right, this is the equation, and it's somewhat like this. This equation is related to this, and the wave function which is made on this back screen. This is a back screen. It is like this. Here it is taken square of, and when you take a square we get a higher wavelength, high amplitude wavelength, high amplitude wave. And at these points, high chance of finding electron. But again, wave nature is only present when wave is not observed. What you will see as fringes on the screen. Here, this area, and this area, and this area, they are known as dark fringes. This is a bright fringe. Okay, and this experiment is Young's double slit experiment. Here we can add one more concept, Huygens principle. What he said, he was one of the persons who contributed to physics a lot. What he said, for waves, let's imagine that in each wave there are circular waves made by something in it which is of infinite amount, called ether. Okay, let me give it a demonstration of it. Let's suppose if we have two lines, if you have line 1, line 2, or wait, we only have line 1. Here, look at this. I have a particle here, I have a particle here, I have a particle here. If I make a circle on it, if I make a circle and I make another circle, I make another circle, now you will see that if you make another line, make an other line at the fronts of each wave. Here Our main topic is the front arc. Important pa is the arc of the circle. And this is for a straight line. But if we have what do you call this, a curved wave, it will be it will look like this, like this, and so on. And this will increase in length, and like this it will have the same thing, but we're increasing the depths, the length. This is how you can illustrate how it's done according 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 to the U principle. Okay, so then what else was it that we have? Yeah, that's it.